Today's session will be split into 3 bits. The first bit was covered slightly in yesterday's session. We're going to talk about what vehicle dynamics is, how HyperWorks plugs into vehicle dynamics, and a brief introduction to suspension design. We will follow it with a demo of Motion View and Motion Solve, which are the simulation tools that we use to analyze suspensions. We will look at some Supra templates that we have created for you, and we will do some sample simulations and post-processing. In the end, we will also talk about design trade-offs during suspension design. So we will talk about how to use Motion View, Motion Solve as a tool to make better suspension designs. And how can you make informed decisions based on data that you get from simulation to make better design. So like this slide shows, we are going to use Motion View primarily to build the model for suspension design, Motion Solve as the solver, which is a multi-body dynamic solver. We will look at the results that the solver produces in Hyperview and Hypergraph, and go ahead to iterate and improve the solution. What we will go through today is the Supra templates for Motion View. These templates are on the Altair website, and they're free to download. These templates are various suspension systems that are used in Supra, commonly used in Supra. These templates are designed for use by you guys who are students who are designing these competitions, vehicle service competitions. In fact, they were created by students who have taken part in international Formula Student competitions. The templates you will see soon are parameterized and modular, and students can use them out of the box, and they can use them to get familiar with multi-body dynamics and how to design suspensions. And we are hoping that you will dig more into the powers of Motion View and Motion Solve to do better design at the end of this session. So these templates are available for download. You don't need to download them right away for this session. I will show you a simple demo of how to use these templates that have been created for Supra, and you can experiment by yourself using Altair software at a later point. Before we go on to the demo, I want to give you a brief introduction to the suspension design process. What we're going to focus today are design of suspension kinematics using half-car models. So this is separating the front from the rear, evaluating them independently, and establishing the characteristics of your software of your suspension based on simulations that you have done using Altair software. These half-car models the front and the rear can later be combined together to form full vehicle models that can do simple and complicated tasks with tire models if the need be. It's going to be important to stress on the fact that you probably need to iterate over your suspension designs. You will decide on a suspension design, you will run a simulation, you will get some results, and you will decide to improve on the results based on what you see. Today's focus is going to be on kinematics and half-car models primarily. Half-car models are the starting point of suspension design. In a half-car model, the chassis is fixed to the ground, as in not allowed to move, and we move the wheels up and down to see how the wheel alignment changes as the wheels move up and down. That is, we observe how the wheel orientations change as the suspension springs compress and rebound. The advantage of half-car models is that they're quick to evaluate, and you can see your results for yourself quickly, and you can try a variety of designs that you may have in mind, one after the other, and get a clear picture of suspension design. Before we move to the demo, I'm again going to take you through a simple SLA suspension, which will be our focus, but you can extend whatever you have learned with respect to the SLA suspension to any other type of suspension that we support. This is, of course, the tire and the wheel. We have the upright and the knuckle, which holds the wheel bearing. Typically, that is defined by 3 points. We'll come to that later. We have the spring. We have what we will call the lower control arm, sometimes known as the A arm or the wishbone. Then the upper control arm, the lower ball joint, and an upper ball joint, about which the steering can rotate. And finally, we have a tie rod on the left, which either provides steering to the vehicle, or in the case of rear suspension, prevents the steering of the rear wheel. And is an important component of suspension design. We are going to focus our analysis on two main analyses. One is the ride analysis, which is simulating the situation when a vehicle hits a bump. In this simulation, as you can see, the chassis of the vehicle is fixed to the ground, and then we are moving the wheels up and down in simulation. Both the left and the right wheels move together, and that's why it's called the ride analysis. And the amount of wheel travel that you see here can be defined as per the user requirement, because different suspension designs require different amount of wheel travel. As per design decisions and the rules. The second analysis we'll be focusing on later is the roll analysis, where both wheels are moved in opposite directions. That is, one wheel moves up, one wheel moves down. Again, the chassis is fixed to the ground, while one wheel goes up and the other goes down. This simulates a situation where we have chassis roll, which means that when a car is turning, you can see the chassis tilt, and why this happens will be explained in a little while. Again, the amount of wheel travel that one wants is user defined. So, with this much background, what we will go through first is a tutorial on how to set up the vehicle models in Motion View and Motion Solve and do simple analysis. After you install Altair HyperWorks, you will see the Altair HyperWorks installation, where you can choose Motion View. Remember, these templates will not function on the student edition of HyperWorks 13.0, and you do need the full edition. After you choose Motion View, the following screen will pop up. This is the Motion View interface. You can also go to this to the website of the Altair HyperWorks EDU Supra, where you will find a zip file containing all the templates that I just talked about, as well as documents describing how to use the template and talking about general vehicle dynamics. I have downloaded the file zipped file from the web page here. and I have extracted all the library from it. So this is what you will see after you have extracted the mbd.zip that you download from the website. Once you load motion view, for starters, you can go to File, Open, Model, and what we're going to do is open a demo model that we have already in the templates. So go to the region where you downloaded the file and extracted it. There will be a folder called Student Vehicle Library, inside which you will have two folders, Baha and Supra. Choose the Supra folder and choose Complete Models, which are the demo models that are made pre-available for you to use. Depending on whether you're trying to simulate the front of the car or the rear of the car, you can choose which of these demo models you want to use. Right now, we will choose the front and hit Open. This will go ahead and load a half vehicle model that you saw in the pictures with a push rod suspension, which I believe is quite common when designing Supra vehicles. It also has a rack and pinion steering, but that both the suspension and the steering can be changed. You will see that this is a double SLA suspension, like the one we saw in the presentation, with the upper control arm, lower control arm, a tie rod, and the steering knuckle. On your left, you will see what we call the browser, which is where all the different subsystems are located. For example, the suspension is located. The suspension systems are located here. The steering systems are located here, and the yellow triangles that you see are analysis. We provide 6 default analysis that you can do on a simple on a half car vehicle. These include kinematic compliance, single wheel analysis where a single wheel is moved up and down, static load analysis, which is just a single load analysis. Ride and roll analysis is what we just spoke about. Steering analysis is only valid for the front SLA suspension, and it involves turning the steering left and right. You can choose which analysis you want to run and activate. For example, if you wanted to run the ride analysis, you click on the ride analysis, right click, and say activate. You will see that analysis gets activated, and now during the run, you will see it run. Let's go first how to determine the design of your suspension. If you go to the front suspension subsystem and open it up, you will see a data set, which is the most important thing that a student needs to edit while doing vehicle suspension design. You will see a data set called vehicle input parameters front. Please remember, all this information is provided in the form of a document in the zip file that you will download, so you don't need to write this down right now. You can just have a look as the demo goes on. So the vehicle input parameters will list all the vehicle parameters related to the front half of the vehicle in this panel section below. So in motion view, we call this section on the left that I have highlighted right now as the browser. This is called the panel, while this is where you can see visualize the vehicle is called the graphics area. So on clicking the vehicle input parameters data set, you will see some parameters that pop up in the panel. You can always use this button here to pop the panel out, and you will see all the associated parameters over here. These parameters are the vehicle parameters or the suspension parameters. For example, your half track width is the determines where your wheel center is the track width of your vehicle. The upper ball joint X, Y, and Z are the X, Y, and Z coordinates of the upper ball joint that you see on this in the suspension. The default values are reasonable values that are available for Supra and a good starting point, but it is encouraged the students go through this design and iterate on their own to make the suspension design even better. However, you can change the upper ball joint X and Y, Z coordinates to move things around. Before I demonstrate that, let's determine what the reference frame is. If you see here you will see the global reference frame. That is the place where that shows that X points towards the back of the car, Z points towards the top of the car, while Y points towards the right side of the driver. This is the standard arrangement that is used by Motion View, and it is strongly recommended that you use the same. It is the minimum requirement we have is that the ZX plane must be the plane of symmetry of the vehicle. Remember, these models are parametric, which means changing things in the data set should be enough for you to move things around in the suspension. Changing things on the left suspension will automatically make the similar change on the right suspension. The template that we have provided is symmetric. You can break the symmetry, however, that involves a few advanced Motion View operations, which you can learn from tutorials. Moving back, let's see the suspension in the front view. Here you see the upper control arm, the lower control arm, and the tie rods. If you go back to the input parameters, suppose you want to move around in your CAD geometry, you will have coordinates of these different suspension pickup points and the upper ball joints and the lower ball joints, which you can enter here. For example, if you want to raise the upper ball joint's height from say 377 to 400, you can do that simply here, and that change will be immediately seen at the back. You can choose to move the Y direction of the upper control arm, and now you can see it becomes shorter. Like that, the lower control arm, the wheel center can be moved around. The other points of interest that need to be moved around are the inboard suspension points, where the chassis and the suspension meet. They are called the suspension pickup points, which are these 2 points that you see here, and these 2 points on the lower control arm. These can be moved around from the dataset through these parameters. The LCA is the lower control arm, front bush X, Y, Z coordinates, the rear bush X, Y, Z coordinates, the upper control arm X, Y, Z coordinates, etc. You can also adjust the location of the spring, the location of the shock absorber, the location of the tie rod, the location of the push rod, the rocker mount, and the push rod inner mount. All of these are vehicle parameters that can be tuned according to your design and the design of your chassis and the design of your suspension. We can see these things move around as you change the numbers in real time. So you can see how the suspension looks like. So I repeat, you need to, on the browser, you need to open the front SLA suspension directory, inside which you will find a data set with vehicle input parameters front. When you pop the panel out, you will see all the parameters that you want to tune, that you possibly want to tune in the vehicle. It is highly recommended that you only change points from this table and not from in the points area directly without doing the advanced motion view tutorials. These should be enough for you to iterate through basic suspension design and multiple configuration. Similarly, each of the analysis, for example, static ride, will also have a data set where you can determine the amount of suspension travel you want to do in the analysis, like we spoke earlier. So the important places where you can tune your model are inside these folders in the data sets. For example, modifying the steering will also involve moving things around in the steering data set, which is called steering input parameters. This is where you can change different locations of the tie rod and the steering wheel and the steering universal joint that you have based on your CAD models or based on your initial design ideas. So in the suspension and the steering section, all the vehicle suspension coordinates are plugged in, and in the static ride section, you go through the analysis that you want to do. For example, if your vehicle is designed to only do 1 inch of travel up and down as per the rules, you would want to change this from 50 mm to whatever distance you want it to move in the up or the down direction. To see how a suspension reacts in these different load conditions, you must run an analysis. Before we run the analysis, let me familiarize you a bit with the run panel. When you click on run, you will see this run button here on the right side is responsible for running the model through a solver. This location here is the location where the solver results will be stored. And it is important that you organize these the locations so that you know your different iterations. The other parameters are again recommended that you do not change them as far as possible or until you know what you're doing. I will open this location folder to find the location where I can run the model. Before I do that, I'll load the default model because I don't know what changes I have made. So we will choose to run the ride analysis first. So I'm going to activate the ride analysis, and you will see that the yellow triangle next to the ride analysis is now active. I will click on the run button, which will bring up the run panel, and I will choose a location where I want to run this. So let's say I choose this folder called Supra demo, create a new folder called webinar, and then let's give it a reasonable name. Let's say front SLA ride iteration 1. And then I simply hit the run button. This is going to invoke the solver, and you can see the solver run. The white pop-up is actually the solver doing the calculations for this particular suspension, and you will see a job complete once once it is done. After you see job complete, you can close this white window, and you will see that the log, animate, and the plot files will show up. The buttons will get activated. First thing you would want to check is the animation to make sure that your vehicle has run correctly. So by clicking on the animate button, the window will split into two, and on the right side of the window, you will see the animation load. You can hit the play button to see the vehicle move up and down. So what you see on your right is a simple analysis done, a ride analysis, where both the wheels move up and down, and you can see that the spring is compressing and expanding, and the tires are changing orientation as they go up and down. How this affects the full vehicle simulation, we will how this affects how the changing wheel orientation affects your suspension design and vehicle handling, we will cover in the later half of today's session. But what you can clearly do now is visualize how your suspension travels up and down at different angles. If you want your suspension to travel more, you can always go back to your model by clicking on it and decide, using the data set in the analysis, to have greater travel. If you want to iterate through design, for example, if you want to say change a location, let's say we want to raise the we want to raise this point here. This point you can see here slightly higher, and see what happens to the suspension after that's done. So we will go to the left model. We will start we will click on the model, go to the vehicle set, and we want to move the upper control arm. So that is UCA front by, let's say, 1 centimeter. So let's make it 294. And there you can see, if that's not, you can see that the suspension has moved slightly. Let's move it more so that it's more evident. Move it to 310. Oops. I'm going to pop it out so that you can see. We'll move this to 310. We will also move the other arm to 310. So now your suspension is slightly different. You have moved the upper control arm slightly above. And then you can hit the run button again. Let's call this iteration 2. Say save. and we're going to run the model again. You will see the white window again pop up. Make sure you change the name, otherwise it is going to overwrite your old result. Once you see job complete, you can close the white window and you can hit the animate button again, and now a new screen will pop up and you can see the new animation, which will probably be very similar to the old one. Now you might be interested in comparing the two. In that case, what you can do is open this file, choose your first iteration, hit the overlay button and click apply. And now you can see both your models loaded one on top of the other. Let's color one of the models entirely in a single color. So now if I hit run, you can see the differences between both their old design and the new design, and how they work. If you have a more drastic change, you will see a bigger change. An animation is always not probably the most interesting thing you want to see, and you might be interested in the plots. There is a plot button here which you can click, and then you can start looking at the different plots the suspension templates create for you. I'm going to press this button here to expand so that you can see the plots. All this process is explained very clearly in the document that comes with the zip file that you download. And over here you can plot different things from the vehicle. For example, if you choose user defined view and you pop out the window, you will see different things you can plot. For example, if you are interested in, say, the toe of the wheel with time, and then you hit apply. So this is how the toe of the wheel is changing with time. But you're usually not interested in how things change with time. You're interested in how things change with displacement. So you can choose the y-axis as displacement. I'm just going to do that. Define. You will find something called wheel vertical displacement, and then I'm going to say plot. What this is the x-axis is now the wheel displacement, the y-axis is now the steering toe, and then you can see how with wheel displacement your toe varies. So as the wheel displaces from 0 to 50, the toe actually comes down. As it goes from 0 to minus 50, that it lowers. The toe initially goes up but then goes down again. These are some of the interesting characteristics that you would want to see in the vehicle. How to interpret this, I will cover them in, again, the second half of today's session. However, there are a whole bunch of interesting things you can plot based on what you are interested in. If you do not understand any of this terminology, all you need to do is go to HyperWorks Help. And in HyperWorks Help, it will clearly explain in Motion View Help what the different parameters are. When you here you go. So you can go to the you can search for suspension design factors and click on this link, and you will see all the different suspension parameters explained. in good detail. So this is the list of parameters. So this is the list of things that you can plot in hypergraph that is listed here, and each of them are explained pretty clearly in the HyperWorks documentation. All you need to do is go to the motion view documentation and then simply search for suspension design factors, or SDF. And each of these things are explained with good clarity. What you can also do is you must remember where you have saved your go back to motion view. If you remember the location where you have stored your results, you can always go back, demo, webinar, and you will find a file called front.sd. You will find whatever the simulation that you ran, this is iteration 1 and iteration 2, and a .sdf file. What you can do is you can open this file in text view that you get with motion that you get with HyperWorks, or you can choose to open it in any notepad software. Open SDF, and you will see whatever you see in the plots in numbers format. So you will and you will also see a few more things that we do not have in the plot. Over here, for example, at time equal to 0, the wheel center displacement was 0, and these are the different parameters with the units that the solver has calculated for you. You can see this for any amount of wheel travel, and you can read from this file if you choose not to look at if you find this easier than looking at the plots. This has also roll steer gradients and stuff that you might be interested in or might come across when you are reading vehicle dynamics textbooks. You can also calculate your Ackermann if you are doing a steering analysis. So if you in this, if you choose the steering analysis, activate it, and run the simulation, you will also have the Ackermann calculations being run for you, and you will get a very good idea of what the Ackermann is. Similarly, you can choose to run roll. So now we are going to run the roll analysis, which again similarly you right click and activate. Once activated, you will see the yellow icon pop become colored, become active. You can again go to the data set and change the amount of travel. Over here right now we are going to move 25 mm up and 25 mm down for the roll analysis. You can change it to a higher number or a lower number, and we similarly just go hit the button and choose the file where you're going to save it. So this is roll iteration 1, save, and then you hit the run button again. What you will see is the white window pop up again, the solver run through, and you will get an animation. So now you can see that the vehicle is actually rolling. One of them is moving up, and the left one is moving down, and the right one is moving up, and now it's changed. Hence, this is the roll analysis. Since this is a Supra car, we don't have too much wheel travel, and hence very little observable up and down motion here. But again, you can go ahead and plot all the different parameters that you want. Similarly, Coming back to motion view, you can choose the steering analysis, where the steering wheel will be turned left and right. I'm going to call it steer iteration 1, and I'm going to run it again, and then you will see that the vehicle actually steers left and right. Similarly, you can always run, you can open the data set of the steering analysis to change any of the parameters that you may be interested in changing. Again, going to hit the animate button, and now you will see the steering action, which is quite predominant. So for all these for all these analysis, you can look at the animation, you can look at the plots, and you can also look at the numbers using the .sdf file. One last thing I want to show before moving on, and let me clear everything, is that we also provide something called a hypergraph template, which is which you can start by which you can open by clicking on this button. This is again explained in the document that is available in the zip file. If you go to the vehicle library, you will see in Supra a folder called hypergraph templates. When you click on that and choose, for example, right now you're looking at the front half of the vehicle, you can choose that. That will pop up what you want. There will pop up where you decide which simulation you want to see. For example, right now we ran a simulation in webinar. Suppose we want to see our ride analysis iteration 1. We choose the .plt file. The plt is the plot file. Open it and say apply. And what will happen now is that all the plots that are interesting with respect to half vehicle analysis front will load at the same time for ease of viewing. So, for example, this is the steering angle plot, which is 0 because we never moved the steering angle. A steering torque plot, the roll, track width, the left caster angle as a function of wheel displacement, if you can see it. So as the wheel moves from 0 to 50, this is the caster angle change. The kingpin inclination changes from 5 degrees to 12 degrees as the vehicle goes from -50 to 50. Similarly, a whole bunch of plots are plotted automatically, and you can look at the plots of your interest. I would highly recommend after you do an analysis that you load the hypergraph template, and because it preloads all the functions that you might be interested in directly plotted with respect to the wheel displacement. Camber angle wheel displacement is probably the most important curve you will look at. What this means is that as the wheel goes from -5, 50 to 50, our camber change is about 3 degrees. This will become, the significance of this will become clear with as this session goes out. But the hypergraph template gives you access to a lot of information, and this is probably the most important tool that you have after you have run the analysis to analyze your results. How do you understand these results will be covered in the session further, but you can also read the documentation I just pointed to, and it will explain what each of these individual things are for you to analyze. This loads about 50 to 60 plots that you might be interested in. It's actually 73. So things like scrub radius, caster trail, mechanical trail, roll angles, wheel center location is available straight out of the bag without you having to do change many things. For every analysis, you can plot these results. Moreover, if you choose to do multiple iterations, you can always load the report again and choose, say, iteration 2, the PST file, I say open, and then I will say overlay, which means that now you will see both your iterations, the plot results, one on top of the other, so that it's very, very easy for you to compare. Since these are 73 plots, they take some time to load, but however, once you will see them load, it's very easy for you to compare. While this loads, let's look at some other stuff that we can do with these models. Let's come back to the main area of our presentation, which is vehicle dynamics, and how do you use the results that we just saw in the demo of the tool to understand the results. So coming back to vehicle dynamics, let's talk about how the tires of the vehicle are going to affect the entire the design of the suspensions of the vehicle. When we talk about vehicle dynamics, we hear a lot of buzzwords which you probably associate if you watch motorsport on TV or read a lot about motorsports. I'm sorry, this is the comparison plot having loaded, so you can see now 2 lines, and then you can compare both the old result and the new result one by one, and then determine which you want to choose. So the overlay feature will also allow you to compare one result to the other directly. So moving beyond the demo, the buzzwords that you see when you do when you read about vehicle dynamics or hear about vehicle dynamics are ride, handling, grip, oversteer, understeer, weight distribution, brake bias. What do these words signify is important to know, but probably the most important thing that a vehicle dynamicist should understand is tires, because tires are the base cause of all the other characteristics that we talk about when we do vehicle dynamic simulation. What are tires? Tires are simply the mechanical connect between the vehicle and the road. The tires are the only point of contact between the vehicle and the road. That means that all the forces that are generated by the vehicle and applied to the road have to go through the tire. In fact, any force that acts on the vehicle that is not aerodynamic in nature originates from the tires, which is why tire is the single most important component you want to know about when you are doing suspension design. So suspension design stems from understanding how a tire works, and the job of the suspension, like we discussed yesterday, is to maintain good contact between the tire and the road. And we will talk about this in more detail today. If you read any textbook or any information about vehicle dynamics, they will always start with a chapter on tires first, which is probably the most complicated one, but it is also at the same time the most important one you need to understand. Before we move to how a tire affects the suspension, we need to know a few things about a tire. The most important one being the contact patch. In fact, the contact patch is the location, is the place on the rubber tire which is in contact with the road. The tire works because of friction between the rubber and the road. The weight of the tire is a normal force that is applied by the road, and that is going to and that is the normal force that the friction acts on. So the weight of the tire deforms the rubber gets flattened at the bottom, and there is a whole patch of the rubber that is in contact with the road, and this is known as the contact patch. In fact, all the tire forces are generated at this contact patch. It is the only point of contact between the tire and the road, hence the only point of contact between the road and the vehicle. So all the forces that act on the vehicle in general originate from the tire contact patch, which is why it is very important to understand how a tire contact patch works when you are doing suspension design. Let's talk about friction. Friction is something that you learn very early in a physics class, probably in before your 10th. The tire is basically a complicated friction model. The tire functions simply because there is friction between the flattened contact patch and the road surface. In normal operation, the contact patch is stationary with respect to the road. As the tire is rolling, the contact patch and the road do not move with respect to one another. If force is applied, the friction starts to oppose it, which means that this is a static friction situation. That the plot you see here on the bottom right is something you would be familiar with. We have friction which is directly proportional to the applied force until it reaches a point which is called the peak static friction, after which we move into the dynamic friction region, and now the rubber of the wheel is now sliding with respect to the road, and this now even if you apply more force, the frictional force applied by the tire is capped at a value that is little less than the peak static friction. If too much force is demanded, so the applied force is the demanded force. So if, for example, if your tire is trying to brake, you will the friction between the contact patch and the road will be in the static region, and the tire will be allowed to stop. But if, for example, the applied brake force becomes too much, the contact patch will move from the static region to the dynamic region. That is, the contact patch will start sliding on the road, which is when the friction becomes less compared to the peak static friction, and you lose grip, which is why actually an anti-lock brake works. However, the important thing to understand here is that you will get your peak static friction only when the rubber is in contact and is stationary with respect to the road. You lose grip when the rubber starts moving with respect to the road. You always this is what a typical tire curve looks like. As the tire force increases, as the force increases, the lateral force, the force generated by the tire also goes up, but it has a maximum limit beyond which it cannot go up. However, if you see, if the normal load on the tire increases, the maximum load also increases, much like friction. When you do a friction model, the normal reaction, if you bring the normal reaction up, the amount of frictional force that can act also goes up. Similarly, in a tire, the same thing happens. If the normal force increases, the friction force also increases. The maximum possible friction force is what you see in this plot here. It is important to note here that the marginal gain that you get, for example, the amount of extra peak force you get when you move from 2000 to 2500 Newton is much bigger than what you get when you move from 6000 to 6500 Newton. We will come to this slightly later. Let's talk more about tire forces. The tire produces forces and movements that act on the vehicle, and these forces and movements can be broken down into different components, like we usually do when we are dealing with forces in different directions in 3D. So first we have the vertical force which acts on the tire, which is the normal force that is basically the vehicle weight being reacted by the tire. Then we have the longitudinal force, which is acting in the acceleration or the braking direction, or towards the front of the tire. We have a lateral force, which is the force that is acting towards the side, which causes the vehicle to turn. We also have a rolling moment, the overturning moment, and an aligning torque, which are also important. So these are torques that act through the tire on the suspension system and determine how a tire reacts to different suspension loads. The next important concept that we need to understand before we understand impact of suspension design on suspension analysis is the friction circle. Although the tire forces can be resolved into components, you have to remember that it is really one force that acts, which means that the magnitude of the force has its limits. What I mean by that, if the tire is applying very, very high longitudinal force, it cannot apply very high lateral force. For example, when you are in, so this is the tire, and now you are applying sorry, there's an audio glitch there. This is the tire, and now you're applying a longitudinal force. You will move along this curve to this point. If at the same time you try and apply a lateral force on the tire, you will move in this region, which is outside the circle, which means the tire will move from the static region to the dynamic region. Hence, your grip will go down, and your tire will start sliding on the road. When the tire starts sliding on the road, the amount of force the tire can exert will go down, the tire wear will go up, and it's not a situation that you want to ideally be in. Understanding this friction circle is probably the most important thing to understand about the tire. Hence, I'm going to repeat myself. The tire produces one force, which is split into components, that is acceleration force and lateral force. These forces have a combined magnitude limit, which means that if you are at maximum lateral force or you're turning with your maximum might, you cannot. If you apply, apply the throttle when you're turning at the limit, you will move outside this circle very quickly and and lose control of your vehicle. That is why when race drivers are driving their cars, they brake before a corner, then turn as fast as they can, and when they exit the corner, they start accelerating. It's because during the corner they are producing max lateral force, and at that time they cannot produce significant acceleration or braking forces. Before we move to trying to understand how vehicle dynamics, how suspension characteristics affect your suspension design, let's understand three important things that you need to know about tire alignment or wheel alignment. First thing is camber. Camber is the angle between the vertical plane of the wheel and the tire in the front view. We are going to investigate how a camber affects the handling of a vehicle in detail soon. But it is really important to understand that tire camber is a very, very important factor determining the characteristics of the vehicle. We have toe, which is the angle by which the wheel points inwards or outwards with respect to the straight car. And then we have caster. It is the angle between the line joining the upper ball joint and the lower ball joint and the vertical in the side view. All these three angles are important to understand. And like I showed you in the demo, all these three parameters are plotted by the motion view motion solve model, and you can see the variation of camber, toe, and caster as the wheel moves up and down. And take notes of your suspension design. This brings us to suspension design trade-offs. And this is where we're going to talk a lot about how one goes about designing a suspension using HyperWorks MED as a tool, Motion View and Motion Solve as a tool. Suspension design involves multiple trade-offs and design decisions. That means you have to make decisions about how you want your vehicle to handle. Based on that, your suspension design will change. There is no one good suspension design. Different requirements, different tracks, different types of cars, different types of drivers will require different types of setups of the suspension. MED simulation is a powerful tool that will assist you in making these decisions. An example of one of these trade-offs is going to be discussed right now. So what we will go through is how camber affects the vehicle handling, and we will also go through how you can tune your vehicle by changing how the camber changes with wheel travel. But you must remember that what we go through is a single example, and it is up to you and your team to make the maximum use of the intuition and the common sense that you have, along with the software and the data it provides and the interpretations of the data to make better decisions, to make better suspensions. Let me repeat. Multi-body dynamic simulation tool, Motion View and Motion Solve is a powerful tool. It is like a hammer, and a good engineer needs to know how to use the hammer. Similarly, MED simulation is a tool, and it is up to you as an engineer to make maximum use of intuition, common sense, the software, the data that the software provides, and the interpretation of the results that you see to make better decisions. Before I move to explaining how the design trade-off works, I need to talk a little bit more about wheel alignment, especially with respect to camber. On the left over here, you see a perfectly vertical tire that is loaded and kept on the ground. You will see a deformation like the one you see on the left tire. If this is on a pressure pad and you measure the pressure at different points of the tire, you will see a plot that goes like this. It gradually goes up, there is a flat plateau, and it goes down. This is the pressure distribution in the contact patch, and it is one of the most important things that you need to understand about how a tire behaves in different camber angles. For example, if you tilt the tire or give the tire camber, and we are talking about a few degrees, 2 degrees or 3 degrees, the situation changes like this. You have more pressure acting on the inside than the outside, because the tire now has an inclination. And now if you measure pressure, it will be something like this, where the inside end of the tire is going to have more pressure. So the pressure distribution is an important factor. Why? Because pressure into the surface area is the normal load that the tire is applying. And like we saw in the plots before, here, that more the normal load, more the capacity of the tire to provide grip. Hence, in this situation, we have a uniformly distributed normal load, which means the entire wheel the entire contact patch has a similar pressure distribution, has similar normal force. Hence, you can apply apply high force till the limit, and at the limit, the entire tire is going to lose contact at the same point of time. However, in the other situation, you will see that the left bit of the tire has lower normal forces, the right bit of the tire has higher normal forces. And as you extract more force out of the tire, you will notice that the left side of the wheel is going to start slipping or skidding before the right side of the wheel because the normal force is lower, which leads you to a situation where half your tire is skidding and half your tire is not, and all sorts of unwanted forces and characteristics. What to give you an to give you intuition of what is happening here, and to give you an understanding of the fact that having even a small camber is going to reduce your grip. Let me give you an analogy. Everybody at some point of time has seen a pencil with a rubber tip at the end, right? Let's do a thought experiment. If you take this pencil, place it vertically like this, and try and rub something, what is going to happen? This is a zero camber pencil with a rubber contact patch between the ground and the pencil. If you try and rub this, rub a sheet of paper, it is going to tear because the pencil is kept perfectly vertical, and the grip that the rubber produces on the paper is very high, and which actually ends up tearing the paper. However, if you tilt it slightly, even slightly, what you will see is that now the paper doesn't tear, but the pencil slides on the paper, which means introducing camber on the pencil rubber tip has decreased the amount of grip. In the pencil situation, you want the grip to be lesser so that the rubber slides on the paper. But in the tire situation, you want to maximize the grip so that there is no sliding between the tire and the road. You are not in the dynamic friction region, but you extract maximum possible grip between the tire and the road. Hence, a zero camber tire is almost always going to give you more grip compared to a slightly cambered tire. Camber can change dramatically with wheel travel, as you can see in this animation here. As this is slightly expanded wheel travel, but as the tire goes up and down, you can see that the camber is changing by a few degrees. The changes with respect to the road are really significant here. Before we move on, let me introduce to one last concept that you need to know to understand further about how camber affects vehicle handling. In the front view, if you extend the lines that join the front, the upper control arm and the lower control arm, and they will meet somewhere in space. This is the point about which the tire is going to move instantaneously. It is called the front view instant center. That is, if the tire is moved up and down right now, it is as if this tire is moving about that point, and the distance between the FVIC and the tire center is the radius of curvature at which this tire moves. The IC can be inside the vehicle, it can be outside the vehicle, it can be on the other side of the vehicle, or it can be at infinity. If the two rods or if the two control arms are exactly parallel, the FVIC is at infinity. What you have to remember is that the IC or the instant center is not stationary. As the wheel moves up and down, the instant center might also change. And the distance of the instant center from the wheel determines how much camber will change when the wheel goes up and down. For example, if the instant center is very close to the wheel, there will be very high change in camber as the wheel goes up and down. If the instant center is far away, and even at infinity, the camber change is very low. So in this example you saw, if you extend the upper and lower control arm, the instant center is very close to the is inside the vehicle, very close to the center of the vehicle. And in this situation, there is very high camber change. In this animation, we have moved the instant center away from the vehicle to a distance further away. And now you can see that the camber change is very, very low. High camber change when the instant center is close, low camber change when the instant center is further away. The instant center, if it's at infinity, that means the arms are parallel and the wheels will always stay parallel to the chassis. Remember, in a half-car simulation, you are keeping the vehicle fixed and moving the tires. Okay, now let's talk about different types of suspensions and different types of choices that you can make with suspension. Suspension is designed such that suspension type 1 is defined such that the instant center is at infinity. This is easy to do. The upper control arm and the lower control arm are parallel. And if you extend the line, those lines never meet. This makes sure that the wheel travel with respect to the chassis is always parallel. And let us consider what happens when you are accelerating and decelerating with this type of suspension. When you accelerate or when you brake suddenly, your vehicle pitches or your vehicle dips. This is the same thing as you hitting the bump, because both your front wheels with respect to the chassis suddenly move up when you slam on the brakes in a sudden manner. And if you look at the cartoon on the right, you will see it actually moved down, but because the IC was at infinity, the wheel camber does not change with respect to the chassis. So during a bump or braking and acceleration, the wheels move up or down together with the chassis. And in suspension type 1, when the IC is at infinity, the camber does not change. That means if your initial camber was 0, even after you are accelerating or you hit a bump, your camber is still 0. This suspension configuration ensures that the wheels are upright with respect to the ground. There is no grip lost due to change in camber. This is the most important takeaway. So when you have suspension type 1 where the ICs meet at infinity, there is no grip lost due to camber when you accelerate, brake or hit a bump. This is probably something that you want because you want to maximize your grip or maximize your friction circle as much as possible. Now let's look at the same suspension. It can be said that the suspension is optimized for straight line events in terms of camber. What does that mean? In a straight line, when you hit a bump or you accelerate and you brake, the contact patch is still flat on the road and you maximize your grip, which means that hence the conclusion that this configuration is a suspension optimized to run in a straight line. Let's see what happens in roll when the CG is at infinity. During cornering, the vehicle sees centrifugal acceleration in the lateral direction, that is the direction towards the left or right of the driver. This causes the vehicle to roll. When a lateral force acts, which is a pseudo force on the vehicle, acts in the sideward direction, what it will do is the normal reaction will change on both the inner and the outer wheel. The inner wheel will have to produce less force and then the outer wheel to balance the new moment because of the centrifugal force, which means that the normal load on the outer wheel will be more than the normal load on the inner wheel, which means that the suspension will be compressed more for the outer wheel, less for the inner wheel, which is with respect to the chassis, one of the wheels goes down, the inner wheel goes down and the outer wheel goes up, and this is the situation of roll. Let's see what happens when I roll. When a roll happens, the one tire goes down, the other tire goes up. You can clearly see the cornering direction here, and the weight transfer has happened towards the outside of the wheel, so it is loaded more. The springs get compressed more there because of the extra load, and that wheel goes up. While there is lesser load on the inner wheel, the springs extend and that wheel goes down. But this is not what really happens, because the two tires, the tire does not go below the road or above the road. What happens is that the entire vehicle actually rolls, which is if you see the animation on your right change, this is what really happens. It's not that one of the tire goes above the ground and one below, but the entire chassis rolls. Now, what you see in this roll situation is that the wheels are still parallel to the chassis, like because the IC being at infinity, but the contact patch is no longer flat. The wheels have actually turned. They have an inclination or they have a camber, and the contact patch is now not uniform, which means you have lost some grip. Let me repeat this again. During roll, the two wheels are still parallel to the chassis, but the entire chassis tilts, which means that there is an inclination angle of each of the tires with respect to the road, and because of this camber, we will actually lose grip. Although the suspension configuration will do very well in acceleration and braking, this will come at the expense of good traction in a corner. Let me explain this concept again. So when you are cornering, roll happens. When roll happens in suspension type 1, when the IC is at infinity, you lose grip because of camber that is caused by the vehicle rolling. Now the question is, can we change this? Because maybe we want a car that does faster in corners. Let's analyze suspension type 2 when IC is close to the CG or IC is inside the vehicle. You can see very clearly in this picture here that the suspension is designed such that the instant center is at the center of the vehicle. What we see here, that the wheel will rotate about an arc that is shown in the picture here. That is a circle about the instant center. There will be relatively large rotation of the tire with respect to the chassis, and you can see that clearly. Now, when we do a roll analysis on this, one of the tire goes down, one of the tire goes up, like we just discussed. But again, this time the wheels are no longer parallel to the chassis because they are moving on this arc. Something like this that you see in the animation, right? The instant center is close to the center of the car, and the wheel is moving along this arc. Again, the wheels, like we see in this picture, do not actually penetrate the ground and go above the ground, but the entire chassis rolls, which means that the entire chassis tilts. But now the suspension is such designed that the arc about which the wheel rotates ensures that during cornering the contact patch is still flat. The entire chassis tilts, but with respect to the road, the contact patch is still flat. This will improve cornering grip. Again, let me repeat. If the instant center is close to the CG, that is suspension type 2, in a roll analysis, we will have more cornering grip because our IC is closer to the center. But this obviously is going to come at the cost of braking and acceleration. Let's see what happens during braking and acceleration. That is the ride analysis. When we do the ride analysis, the vehicle actually goes down, the wheels still move about the arc, the chassis is still upright with respect to the ground, and now there is inclination angle that shows up. Grip is lost in straight line events. The extra cornering speed that can be generated because the contact patch stays flat has actually come at the expense of straight line acceleration. You can see this happening in the ride analysis straight away. If the suspension moves up and down together, there is a huge camber angle induced and the grip goes down. Now the question is, which is the better suspension? Suspension type A or suspension type B? It is a difficult question to answer. It is a decision that you need to make. Do you want your chassis do you want your vehicle to be faster on the corner or faster in a straight line? Do you want more points in acceleration or more points in maneuverability? If the endurance track has more corners than straights, maybe you want to tilt towards something with higher cornering speeds and lower straight line speeds. These are the questions that you need to ask yourself to decide which way do you want to go. And it is not a binary answer either. You can choose something that is between suspension type A and suspension type B, or suspension type 1 and suspension type 2. How can you choose something like this? By iterating through different vehicle designs using motion view and motion solve. You can try different configurations, different IC locations in your model in motion view and motion solve. You can say try 5 different. You will get different camber curves with respect to your with respect to one another, and then you can make a smart choice based on what you want, based on the answer to this question. What does the path look like? Does your car spend more time in corners? Does your car lack acceleration? Maybe you have an underpowered engine and you want to make up for the underpowered engine by having a suspension that is closer to type 1. So you will have more power in the straights, but at the cost of corners. Do you need to optimize maximum cornering speed or the maximum acceleration? You don't. What you need to do is maximize your lap time. And if you try and maximize your lap time, you will maximize the amount of points at the competition, and hence you will reach some middle ground between acceleration and cornering speed, and that will be where you want your car to be. Clever designs are possible. With minor adjustments in the suspension configuration, you can go from suspension type 1 to suspension type 2. Maybe by changing changing one mounting point, you can have 2 mounting points on the chassis. For acceleration, you choose one, and for your maneuverability event, you choose another one, and your suspension characteristics changes accordingly. What you really want to do is make the wheel alignment change, make them to your advantage. You also and motion view and motion solve is going to be a very, very powerful tool. Like you saw, one simulation took about 30 seconds to run. So you can, in an hour, you can probably do about 100 simulations and then compare your results. And you can choose multiple configurations and decide which suspension design factor you want to, or which suspension type you want to choose. Now remember that this analysis that we just conducted is an example. We did this for camber versus how your camber curve or how your camber changes with respect to wheel travel is affecting the acceleration and cornering performance of the vehicle. In a similar way, toe, caster, scrub radius, everything that you have affects how your vehicle is going to handle during dynamic events. And if you go through a similar study with all of these parameters, you are heading towards a better and better suspension design. Obviously, you cannot spend all the time doing this. Hence, you have to decide on some goals beforehand. What are your suspension goals? And then choose the different, choose a suspension from the hundreds and 200s and 300s of iterations that you will do that best fits your goals. The goals can be to do well in acceleration. The goals can be to do well in endurance. The goal can be to design a suspension that is going to give you the maximum points at the competition. I hope this gives you a good idea, or through an example, of how you can use HyperWorks, motion view and motion solve to optimize your suspension design at Supra. And also understand why it is a powerful tool to do so. Let us take a step back and look at the HyperWorks again, and what information you have from HyperWorks. You have the MDL file, which is the model data you have the H3D file, which is the animation, and these are the files that you will see are created here. The H3D, the MRF, the PLT, the XML. The XML is your model. The log file is something that you want to keep. In case you see a problem with your simulation and you want to consult somebody else, or you want to post on a forum, or you want to write to Altair, you should attach the log with it, and we will see what you have run in the model, and we can get a better idea of what you're trying to do and what possible thing has gone wrong with your analysis. The PLT file is the plot data, the H3D file is the animation. You can load the animation in Hyperview, PLT in Hypergraph, and SDF in text view. All these three things I have shown to you a little while ago how to do. So it's important to understand the different information you will get from all these three files. Bringing back motion view, there are a few other things that I need to show you. Let's go to motion view. Not everybody will be using push rod suspension, which means you would probably want to change the type of suspension being used. So let's go back to the vehicle library and load the model that we have loaded, the front half car. Once this is loaded with all the different analysis on your left, and suppose you have decided that your vehicle does not need a push rod configuration and you want a direct actuation configuration, what you can do is choose the suspension that you don't want. In case this is front SLA, right click on it and say delete. When you hit delete, you can get rid of this suspension. And then eventually load another type of suspension. So the suspension is now gone. Now I will click on model, import. All of this is explained in the document provided in the zip file. And you can choose another configuration. For example, I'm going to choose a suspension for SLA. And what you will see on hitting import is an SLA suspension load. Now this is the direct actuation suspension you are looking for. After this is loaded, all you need to do is right click on the model, say apply attachment candidates, and say auto resolve attachments. What this is going to do is going to hook your model up with the new type of suspension. This procedure is clearly explained again in the document. You can do the same thing with this type of suspension. The front SLA will also have a data set, and you can change all the parameters that you want to, depending on your design. When you are satisfied with your design and you choose the correct analysis you want to run, you activate the correct analysis, say run, and choose your location, which was for me demo webinar. Let's call this front SLA direct, right iteration 1. Save. And now you're going to see this type of suspension run. So the models that we have are modular, and you can swap one type of suspension for another type of suspension if the need be. You can also compare one type of suspension with the other using the hypergraph templates that I just showed you. Now if I click on animate, you will see this. You will see the direct actuation happening. Similarly, you can load whatever reports that you want, like you've been doing for the hypergraph. Yes. Similarly, you can do different analysis. If you want to analyze the steering and how the camber changes with steering, which is your bump steer characteristics, you can look from here. We also have the rear half car model where you can design the rear suspension with different configurations. In this case, we have the example that we have given is pull rod suspension. However, you can change this for a push rod suspension or a direct actuation as well, like I just demoed, and the explanation in the document provided. The rear suspension obviously does not have a steering, and instead you will see a fixed tie rod in the model that is located here. So the vehicle library that Altair provides has some basic model setup. If you're looking at advanced modeling, I would highly recommend you go to the help section in desktop motion view and go through the motion view tutorials, and they will give you an idea of how, which are at the bottom here, and they will give you an idea of how these models work in different situations. And you can also go ahead and create your own templates or your own types of suspensions if required. If you get stuck anywhere, you're open. You're welcome to write to us. So that concludes the demo of the vehicle dynamics tool that Altair provides. Again, remember, MDL file is the model, SAEINDIA file is the animation that you can view. You can plot results in hypergraph. We also have the templates where you don't actually need to plot the results individually, but if you choose the plot file with the template, all the relevant plots will be done simultaneously, and then you can choose which you want to look at. This also has the option of overlaying, where you can overlay one over the other and figure out which you like better. We also have capability of doing full vehicle models, which basically is you design the front half and the rear half, put them together, and then actually run the vehicles in in simulation through different analysis. Doing this, is not going to be covered right now, but there are a few videos available which explain how you do this. The document that is available, the help document or the tutorial document that is available in the zip file also explains this procedure. We can do, so after you have assembled both the front and rear vehicles, you can do this kind of simulation where you can see the car run beforehand. But I would recommend that you spend most of your time doing the suspension iterations and understanding the effects of camber, toe, caster, scrub radius, and the other things on the handling of your vehicle, like we went through the camber example right now. HyperWorks can also do load extraction. So if you see the SDF file, you will also have information about load that each of these components is seeing. Let me load the file. Where did I run the models? Demo, webinar. When you look at it, you will also get information such like wheel center stiffness, so that how stiff the wheel is, how much are the different forces that are applied by the tire, what are the wheel rate, ride rate, suspension roll rate. All of these things are readily available in this file here, and you can make sense out of these. And from these roll rates, you can also determine the forces that are acting on the on the vehicle in steady state while you're designing the other components that you might be interested in. For example, if you know the roll rate, then you can say that for X amount of acceleration, you know the amount of roll that you are going to have. Hence, you know the camber change. Hence, you know the force that the tire can extract, and you can do your force calculations of the hub or the upright based on that. Again, this is an advanced use case, and you will have to go through the motion view tutorials to see how this works. And like you can see in these animations, the motion view motion solver can do a whole bunch of events and analysis that can help you understand the dynamics of your car in more detail. So this is the brief. This is what we're going to cover in the vehicle dynamics module of the training that we have, and hopefully this you can use motion view and motion solve as a tool like we described today through demo to do better suspension analysis and suspension simulation. So thank you for attending today. That's the end of today's session.